If you're sitting in this room, you are very likely already familiar with the rate that 1 in 36 children in the United States has a diagnosis of autism. There we go. And that of those children with an autism spectrum diagnosis, roughly 30% will not develop language even as adults. Even though we now as a field are fairly reliable at being able to diagnose this disorder between 18 and 24 months, the median age of diagnosis in the United States isn't until 4.9 years. And that gap leads to a lot of questions when I'm in clinic from families about, does my child have autism? Is my child going to learn to speak? And there's a significant gap between what we should be able to tell these families and what we currently are able to do. Part of that issue is the access to diagnostic evaluations, and part of what we need to do a better job is on this early screening and identifying those kids who really need those formal evaluations. If we knew earlier, we could be getting these kids better access to services earlier. We could be getting them into more research studies. And those studies might help us identify what some of the underlying causes are in the challenges that we see in children with autism spectrum disorders. So as a field, one way that we approach this challenge is to look at the baby siblings of autistic children, the babies that are at elevated likelihood for a diagnosis. Even when we do these studies, we need 5 times our target sample to get enough children to study the question of interest. And in a population as heterogeneous as autism, we need huge samples to draw any meaningful conclusions about what's going on here. Next slide. So since 2020, with generous support from the Simons Foundation, I have had the great honor of coordinating a team of clinicians and researchers and computer vision experts who all came together to help address these questions with something we call the Remote Infant Studies of Early Learning. Our RISE battery and consortium is the significant lift of more than 20 people who have been involved with this project. And I get to be the lucky one presenting this work today on behalf of all of these folks. Next slide. Traditionally, when we look at what is going on with babies, we can't ask them what they think of something. We have to find other ways of understanding how they're responding to stimuli. So historically, we bring them into the lab, we show them pictures or videos on a screen, and we watch in which direction for how long they look. Before all of us went into our Zoom rooms, researchers at MIT had developed a platform called Look It, now called Children Helping Science, that allows us to bring those traditional lab-based studies into the home. And we are able now to show these traditional studies to babies at home and securely capture their responses to those stimuli that we're showing them. Using computer vision and AI, we can now tell automatically, using open access software that tells us which direction for how long that baby is looking, using machine learning. Next slide, thank you. So the RISE battery takes about 20 minutes. Babies are doing this at home, asynchronously, whenever convenient for them. And currently this consists of about 7 tasks that study domains we know are relevant to later developmental outcomes. Attention, memory, learning, multimodal processing, language, numeracy, and social cognition are all aspects of developmental milestones that we know predict later outcomes. Next slide. This approach isn't without its challenges. When we do these studies in the home, sometimes the baby is too low. Sometimes the baby is too high. Sometimes we don't have a great connection. Sometimes we get sibling interference. Sometimes we need a nap. And sometimes it's all of the above. But over the years, we've gotten better at collecting this type of data. Next slide, please. So what you're going to see here is, I'm not going to show you all of our tasks, but this is our social attention task. You can go ahead and play it. This is a an abstract geometric figure on one side of the screen, dancing children on the other. This is based on work from Karen Pierce and colleagues. And what you're seeing on the left here is the baby at home. The mom may well be tired, but we have actually asked them to close their eyes or look away or put on sunglasses. And that green arrow tells you whether the baby is looking to the left or the right, and the number under that arrow tells you with what confidence the eye catcher software has made that determination. Based on previous work, we're expecting our low likelihood babies, those without a family history of autism, to be looking at that social side of the screen. We can go to the next slide. And that is indeed what we are seeing so far in our low likelihood sample. I'm going to take a minute to walk through this because you'll see a couple of figures like this. On the y-axis, or the vertical axis here, you're seeing the proportion of looks to that social side of the screen. The red dotted line here is chance, meaning they were looking equally at the social or non-social sides of the screen. And each one of those little dots is an infant. So in our 6-month sample, we currently have 39 babies in this group, and in our 12-month sample, there's 48 babies. And the fact that that big pink blob is above the red dotted line shows us that they are reliably looking at that social side of the screen when we're showing them these videos at home at both 6 and 12 months. Next slide, please. This is some preliminary data. We are still running the analysis on our baby SIBs. These are with elevated likelihood due to the presence of an autistic sibling. And here what we're seeing is that the 6-month-olds are reliably looking to that social side of the screen, but by 12 months, you can click twice forward, they're not. And that is consistent with a couple of other groups' findings in the baby SIBS literature that we see somewhat typical looking performance at 6 months, but this divergence happening between that 6 and 12-month period. Next slide. What this tells us is that computer vision could help us screen for autism in young babies. If the babies are not looking at that social side of the screen, those may be the ones we need to get into those more formal assessments. Another task we look at is whether they're recognizing faces. This is about memory, and we can play this video. What you'll see is quite boring. We warn the parents that we're going to be showing them 2 identical faces on the screen. Their connection is not broken. This video isn't actually playing, but you would see the baby getting bored if it were. And we also do this with something called fribbles. These are non-social stimuli that are designed to be as complex as faces. They have the same number of features as faces, but they don't have that social component to them. There's that baby getting bored. Next slide. So what we're seeing here, one more, is a reliable preference for the novel video. Sorry, that video would have shown you that after about 20 seconds of the same face, and we've bored them thoroughly, we change it up, and they see a novel face on one side and the same face. If they have created a memory for the face that they were already trained on, then we should expect them to be looking at that novel face. And that is indeed what we see at 6 and 12 months in both the faces and fribbles condition. We are getting reliable attention, so each of those dots and the pink blobs are above that red dotted line, suggesting that we are getting the expected result here as well. Next slide. Keep going. There it is. In our baby SIBs, we are showing novelty preference again at 6 months in both the faces and fribbles condition. You can advance a few slides here. There we go. Not in the faces for the 12-month-olds. Again, this is consistent with what we might expect. This is very early in the stages, but if this moves forward in this same pattern, it would be consistent with this notion that we're seeing divergence in these babies starting to look more autistic by 12 months. Takeaway message here is that computer vision could help us understand how memory develops in children with autism. Next slide.
Look at the foot.
You can stop that one. This is our word recognition task or word comprehension.
Look at the...
Banana, I believe is what she was going to say. The comparison here is, are they looking at the banana more when we say look at the banana than when we say look at the hair? If kids are reliably recognizing these words, we should see increased attention to that target word when it's the target object. The benefit of doing it this way is we don't need any overt responses. We don't need the babies to tell us anything. We don't need them to point at anything. We're able to tell from their gaze direction whether they're understanding these words. Next slide, please. What we are seeing, you can click through, is what we expect in the low likelihood babies, that they're not necessarily reliable at 6 months in recognizing these very familiar baby words, but by 12 months they are. Next slide. Importantly, this is related to what parents are telling us about their child's language acquisition, that the way the baby is understanding, producing, and communicating per parent report is consistent with the data that we're getting in this remote setting. Next slide. And our baby SIBs are not necessarily showing this pattern, which is consistent with the idea that we're not just going to see in this baby SIB population higher rates of autism, but also potentially more language delays. So computer vision here may help us understand how language is developing in autism. Next slide. So this is early stages of this project. We're still in the exploratory phase, but this approach has promise, I think, for helping us answer some really big questions. Is it autism in these children? Which skills are going to be impaired? Which are going to remain intact is also, I think, an interesting question. Is language coming online? And critically, does this child need intervention? If we could get intervention in place, we might be able to be doing a whole lot more for these kids before that 4.9-year mark when they're about to enter school. And that would be huge. Next slide, please. We are still recruiting babies. If you happen to know of any 5 to 7 month olds or 11 to 13 month olds, we'd love to have them. We're in between phases, but in the next 2 weeks, you'll see a new study pop up on that site. And I'll put in a little plug, next slide please, for our meeting on language and autism. This is an event that Autism Science Foundation and the Simons Foundation have generously sponsored since we started this a few years ago, and we would love to see you all there. Our next one is in Atlanta in 2026. And I will, next slide please, thank the incredible collaborators on this project, the participants and their families, the Simons Foundation for the funding that got this off the ground, and the Autism Science Foundation for the funding for my postdoc many, many years ago. It is the reason that I'm in the field, and these fellowships for student trainees makes a huge difference, and I definitely wouldn't be here if that didn't exist. So thank you very much. Thank you for your time.
Sorry, I have a quick question.
Sure.
What is the meaning behind, or why would there be a difference in faces but not fribbles?
Yeah, so we know that social stimuli can be a little more challenging for a lot of autistic children than for those without autism. And what we're interested in that task is whether we might see challenges in the encoding of those memories that are specific to those social stimuli. We might expect the autistic children to do just fine on those fribbles, even though that's just as hard. It's got the same number of features as the face. It doesn't have that social component. So we might see a divergence there, which is what is hinted at in these very early data.
And so I know you're following the SIBs, right?
Yes.
To diagnose.
Oh, thank you. Yes, we thank you again to the Simons Foundation. We are now going to be able to follow these babies.
Yay.
Yes.
But for the typically developing group, the one that didn't have a high likelihood, how long are they normally followed in studies like this using Look It?
Yeah, so this is the first I know using this approach on Look It, so I don't think there's a general answer to that just yet. But we can make a diagnosis between 18 and 24 months, so we'd want to follow between 2 to 3 years if we could.
And one last question after listening to Bob's presentation.
Yes,
are you considering including any other besides, eye tracking in terms of the
Yeah, so you were predicting my question for Bob later, which is, can we take some of these videos and run them through that software? Yeah, we are pursuing a couple of different questions. I think we've done work before showing that vocalizations, even in these very short administrations, what the babies produce in that context can give us valuable information about diagnosis later on. So things like that are definitely under consideration. Thank you. Thanks so much.